Hello everyone! Today we delve into the fascinating realm of large language models, LLMs and generative AI, exploring the workings of models like ChatGPT. From understanding language modeling to decoding algorithms, we will uncover the underlying mechanisms that empower these models to generate current and contextual relevant content. So let's just start with generative AI. Generative AI is not a new technology. It goes back to the 1960s when it was used for chatbots. Then in 2014, with the introduction of GAN, which is a machine learning algorithm, it was possible to produce even more realistic but fake images. In 2017, Transformers, a Google product, changed language models by introducing an attention-based encoder-decoder architecture. We will take a closer look on this later. But what is actually generative AI? Generative AI is an artificial intelligence technology. It involves the creation of new and meaningful content by learning patterns and structures from existing data. For example, images, text, coding, audio, and other kinds of content. In the context of language, this often involves language modeling and sequence generation. So let's just start with language modeling. Imagine you're building a speech recognition system and you hear the sentence 60 minutes is 1 hour. What did you hear? The first sentence or the second one? Obviously, you're going to think automatically that it's the first sentence. But for a system, it cannot know just like that. It actually needs probability, and based on it, it can choose which one is the correct one. And in this example, obviously the first sentence is the one that the system's gonna choose. For sequence generation, it involves predicting and generating the next element in a sequence of words. For example, in the sentence, the cat climbed the. The goal is to predict the missing word based on context. In this case, the system can give like too many options, and same thing, based on probability, it can choose which one that fits more. Now let's talk about large language models. The LLM produces human-like text-based material by utilizing natural language processing, the NLP. Unlike generative AI models, which are widely applicable across various creative domains, LLMs are made especially for managing language-related activities. Because memory units are built into their structures, these large models can comprehend context and retain information after retrieving and storing pertinent data that can formulate correct and cohesive responses within the given context. We can actually talk about the LLM into three parts. We have the data, the architecture, and the training. For the data, the LLM uses terabytes of data, and for 1 gigabyte of a text file, we can have 178 million of words. So imagine having 1 terabyte. That's too many words, and we're gonna have a large amount of data. And actually, that's the meaning of the word large in the title in the large language modeling. For the architecture, the LLM uses transformers, and we're gonna talk about it in 2 seconds. For the training part, this architecture, the transformers, are gonna be trained on all the data that we have. When I'm gonna talk about transformers, a lot of people are gonna think that I'm talking about this. Unfortunately, it's not. It is something strong, but it is this thing. The architecture of the transformers is looking like it's divided in two. On the left side, we can have the encoder, and on the right side, there is the decoder. Let's start with the encoder. When you can see down, you can see there is an input, and there is something called input embedding. The input embedding is meant because the transformers is using neural networks, and neural networks don't actually understand words. They need numbers. So our input has to be transformed from words into numbers. When we get more insight of the input embedding, we can have an example. We have a sentence, how are you? The sentence words are gonna be divided the how, are, you, and there is the EOS, and they're all called tokens. The EOS is signification of the end of the sentence, end of sequence. We can also have the activation function. In this example, there's only two activation functions, and we have the weights. When we want to know the number of the word how, we're gonna actually have two because we're using two activation functions, and the word how have two weights. So when we want to know the number that's going to represent the word how, we're going to put 1 for how and 0 for the rest. Then we're going to multiply the 1 by the weights that it has, and the others are also going to be multiplied, but it's going to be a 0. For the input of the activation function that we have, that's going to be 1.87, 0, 0, and 0. So we can see that the output of our function will be 1.87, which means that the fx equals x. The same thing is going to be happening with the other weight and the other function. And that's how we will end up with the two numbers that are representing how. Same thing goes for the others. Whenever we want to have the numbers that are going to represent each of these words, we just want to put 1 on the word that we need and zeros for the rest. The positional encoding. For this part, you're probably going to wonder why the position of the word matters. I'm going to give you an example. We have this sentence, Sam eats fries. That's cool, that's good, but what if fries eats Sam? That's a bit confusing. So in this case, we know that the position of words are important. For the positional encoding, I took the same sentence as an example to explain how it works. I created 4 words embedding values per word, as you can see here. The numbers that represent the word will be added to the number that represent the word order. To get those numbers, as you can see here, we use the sequence of alternation sine and cosine squiggles. So for example, for the first word how, we refer it as the green one. So for 0, when it's the first word, it's 0. For the second one, it is minus 0.9. For the third one, it is also minus 0.9, etc. For the second word, it's represented by the yellow one. On the first word, it is a 1. On the second, it is 0.4. You can see it can goes like this. And on the third, it is minus 0.9. And the same thing goes for the others. After we add those numbers, we can have the final number which present the position number of the words. Now we will pass to the multi-headed attention, self-attention. This is, for example, the vector of the word how. It will break down into 3 component vectors. Each vector will be broken up into 2 separate pieces, and each piece will be part of creating the attention unit. Those component vectors are called Q, K, and V. Query vector, the key vector, and the value. The Q will be representing what I'm looking for. The K will be what I can offer, and the V represents what I actually offer. The attention unit will also receive other heads from the other words. Then we're going to have the queries and keys undergo a dot product matrix multiplication to produce a score matrix. The scoring matrix establishes the appropriate level of focus for each word compared to other words. As a result, every word in the time step will have the score that correlates with other words. The greater focus, the higher the score. So the mapping of the queries to the keys looks like this. After that, the scores are reduced by dividing by the square root of the query in key dimensions. This makes it possible for gradients to be more stable because multiplying values can have explosive impact. Subsequently, the attention weights are obtained by taking the softmax of the scale score, given probability values ranging from 0 to 1. Softmaxing elevates higher scores while lowering lower scores has the opposite effect. This gives the model greater assurance regarding the terms it should consider. The output vector is now obtained by multiplying the attention weights by the value vector. The value of the words the model learns will remain more significant for higher softmax scores. The lower scores will overpower the irrelevant words. The output of it is then fed into a linear layer for processing. Before using self-attention, we must divide the query key in value into n vectors in order to turn this into a multi-headed attention computation. After that, each split vector goes through the self-attention process independently. We refer to each self-attention process as a head. An output vector from each head is concatenated into a single vector before passing through the last linear layer. The encoder model will have more representation power since each head will learn something new. The initial position input embedding is added with the multi-headed attention output vector. We refer to this as a residual connection. The residual connection's output goes through layer normalization. A pointwise feed-forward network is used to project the normalized residual output for additional processing. A ReLU activation sits between a couple of linear layers to form the pointwise feed-forward network. After that, the output is once more added to the pointwise feed-forward network input and further normalized. By enabling gradients to pass through the network directly, the residual connections help in network training. The network is stabilized by the use of layer normalizations, which significantly reduces the amount of training time required. The attention outputs are projected using the pointwise feed-forward layer, which may result in a richer representation. The encoder part is over. Now we will pass to the decoder layer. The role of the decoder is to produce text sequences. The sublayer of the encoder and the decoder are similar. It features a pointwise feed-forward layer, two multi-headed attention layer normalization after each sublayer, and residual connections. These sublayers function differently for each multi-headed attention layer, although they behave similarly to the encoder's layers. We also have a linear layer that serves as a classifier and a softmax that extracts word probabilities constitute the decoder. The encoders and decoders beginning are nearly identical. To update positional embeddings, the input passes between an embedding layer and a positional encoding layer. The first multi-head attention layer receives the positional embeddings and uses them to calculate the attention scores for the input from the decoder. This attention layer has multiple heads and functions a little differently. As the decoder is autoregressive, it constructs the sequence word by word. Therefore, you must stop it from conditioning to subsequent tokens. For instance, you shouldn't be able to utilize the word fine while calculating attention ratings from the word am, because it is a future term that was formed after. Only the words that came before and the word am should be accessible to it. They can only focus on the words that came before them, and this also applies to all other words. The mask is a matrix that's the same size as the attention scores filled with values of zeros and negative infinities. When you add the mask to the scaled attention scores, you get a matrix of the scores with the top right triangle filled with negativity infinities. The mask is used because when taking the softmax of the masked scores, the negative infinities are eliminated, resulting in zero attention scores for tokens that come after. As you can see in the figure, the attention scores for M has values for itself and all words before it, but is zero for the word fine. This essentially tells the model to put no focus on those words. The second layer of multi-headed attention, the queries and keys are the encoder output for this layer, and the values are the first multi-headed attention layer outputs. By matching the information from the encoder and the decoder, this method enables the decoder to determine which encoder input is important enough to focus on. A pointwise feed-forward layer processes the output of the second multi-headed attention before being sent to a different processing layer. One last linear layer serves as a classifier for the output of the final pointwise feed-forward layer. The size of the classifier corresponds to the total number of classes. For instance, the output of the classifier will have a size of 10,000 if you have 10,000 classes for 10,000 words. After that, a softmax layer receives the classifier output and generates probability ratings ranging from 0 to 1. Our expected word is equivalent to the index with the highest probability score. The decoder then takes the output, added to the list of decoder input, and continues decoding again until a token is predicted. For our case, the highest probability prediction is the final class, which is assigned to the end token. The decoder can also be stacked n layers high, each layer taking in inputs from the encoder and the layers before it. By stacking the layers, the model can learn to extract and focus on different combinations of attention from its attention heads, potentially boosting its predictive power. And that's how transformers work. Now we will talk about the ChatGPT. But first, let's talk about the GPT-3 language model. OpenAI developed the GPT-3 Generative Pre-trained Transformer 3 language model. After being trained on massive text data sets including hundreds of billions of words, the 175 billion parameters deep learning model can produce text that is similar to that of a human. GPT uses an unmodified transformer decoder. The encoder attention part is absent. The graphics, as you can see, gives a visual representation of this. To construct the GPT, GPT-2, and GPT-3 transformer decoder, blocks are used. In contrast, BERT makes use of transformer encoder blocks. Massive 170 gigabytes of internet text datasets were used to train GPT-3. With 175 billion parameters, 100 times GPT-2, it was the largest neural network when it was first released. Each of the 96 attention blocks in GPT-3 has 96 attention heads. Next word prediction, a type of unsupervised training in which the computer predicts the word that will appear in a phrase, was used to train this version of GPT-3. The input sequence for GPT-3 is fixed at 2048 words. Short sequences can still be passed in as an input, but simply placing empty places with empty values. The GPT result is a sequence of guesses, length 2048, with the probability for each possible word, not simply a single guess. One for every next place in the sequence. However, we usually just consider the guess for the final word in the sequence when producing text. After taking a look at GPT, now we can talk about ChatGPT. ChatGPT was modified and improved using both supervised and reinforcement learning methods with the assistance of a human trainer. ChatGPT also has 176 billion parameters, same as GPT-3 model. The learning includes 3 steps: supervised fine-tuning of GPT 3.5 model, reward model, proximal policy optimization. Let's start with the first step. A pre-trained GPT-3 model is used in the first step, and a supervised dataset will be created to help labelers refine the model. The input prompts were collected from the real user entries, and the model produced several answers in response to those questions. After that, the labelers produced a suitable response to the input prompts, indicating how they wanted those prompts to be replied. This new supervised dataset was subsequently used to refine the GPT-3 model, resulting in the GPT 3.5 model. In the second step, the SFT 3.5 model produces improved replies to input requests. In this step, the SFT model is employed. Various input prompt queries are fed into the refined model, and multiple replies, 4 to 7, are created for each input or prompt. The labeler then chooses a reward for each outcome, and the award corresponds with the response's quality about the prompt. The labeler ranks the output from best to worst. After that, we may train a reward model using this data. The user prompt and one of the generated responses will be the input for a reward, and the output will be a scalar value that indicates the response's quality in relation to the input prompt. Also, the reward model is trained using established rankings. You're probably gonna wonder how the trainers give their review. There will be a screen for each labeler where they must enter their rating and provide a physiological explanation for the response. The ranking will be determined by comparing the labeler's similar physiological justification. A reward model will be trained based on these ratings. Also, you're probably wondering how the system is gonna give us multiple answers. Well, GPT uses different decoding strategies like nucleus sampling, temperature sampling, and top K sampling. Based on these strategies, it will generate different outputs for every time step. These are parameters which can be further tuned. So, for example, for the sentence today we will have French. For the top K, a K will be 10 for fries. For the nucleus, the P will be 0.9 for bread. And for temperature, it's going to be T equal 0.7 for toast. And for greedy, which is the normal probability, it will give us toast. Passing to the third step, this stage involves feeding unknown input sequences into the clone SFT model that we obtained in step 1. The model will produce a response according to the prompt for input. We analyze the output reward to adjust the parameters of our SFT model after passing the response to our reward model that we obtained in step 2 to determine how well written the response was for that input prompt. This is how reinforcement learning will be used to add more traits and behavior that are similar to those of humans into our SFT model. So as you can see, we have a new prompt is sampled from the dataset. Write a story about otters. The PPO model is initialized from the supervised policy. The policy generates an output, once upon a time. Then the reward model calculates a reward for the output. The reward is used to update the policy using PPO. Well, it looks like it's easy, so let's make it a bit complicated. We're gonna have a question, what is for breakfast? For GPT 3.5. At T0, it's gonna start writing today, and at T5, it will get to today I will have French toast. The trained reward model will receive the response from the model after receiving it. This will indicate how well the response complies with the input sequence. The parameters of the clone SFT model can be updated with the help of this reward. The PPT proximal policy optimization. The GPT model was upgraded. The goal of the PPO is to maximize the total reward of responses generated from the model by including reward in the loss. If the response is very good, the product of R and advantage function A will be large. If the advantage function will be negative, the response will be bad. Then we update the gradient with help of optimizers. This is the likelihood function to maximize. We have the RT, which are the reward with new parameters and the old parameters. We have the proportional to reward function, and we have in the last part, clip is to ensure changes of parameters isn't too large. Thank you so much for your attention. I hope everything was clean and well explained. You can find all the references that I followed here in this slide. Thank you so much again, and goodbye.